All right. So our today's third speaker is Zhicheng Yang from Peking University. Zhicheng will talk about entanglement dynamics, magic highway. I think this is pretty nice. That's welcome our speaker.
Okay. Okay. Thank you. Just thank the organizer. I think he's been working really hard for this nice conference. I am Zhicheng from Peking University, and today I will be talking about this recent work that we just put up a few months ago. Probably will change the title at some point because I got some complaints. Yeah, it's basically to study the interplay between magic and entanglement in a sort of dynamical setting. And the message really simple, and also technically it's very simple. So I think it'll probably only take me like 40 minutes, but I guess also people probably won't complain about that. So let's see how it goes. Yeah, let me just begin by acknowledging the collaborators. So Zongyue is actually an amazing undergrad at Peking University. Undergrad, yeah. So he actually did all the heavy lifting in this work. And then the other collaborator is Charles Cao from Virginia Tech. And he is, I mean, he has more experience with quantum information in general, and especially quantum magic. So, okay. So maybe just to zoom out a little bit. So this has to do with, at a more fundamental level, you could ask, what makes quantum quantum, right? And maybe, the first answer that pops up in our mind is probably this notion of quantum entanglement. So basically, this is rooted in the linear superpositions of quantum states, which manifests as a sort of non-classical correlations. And then this is nicely encoded in various correlations in terms of the Bell's inequality and its variance. And this is also important for a variety of communication tasks, for example, involving quantum teleportation, and is also essential for demonstrating quantum advantages. And also, this notion of quantum entanglement has been, of interest to a broad community other than quantum information, including condensed matter theories, for example. It plays an essential role in the characterization of topological order, and also, more recently in this field of non-equilibrium dynamics, the dynamics of entanglement also tells us some information about quantum chaos and information scrambling in quantum many-body systems. And also, since this quantum entanglement is sort of it's sort of beyond classical operation, and you can whenever you have something that is costly, you can sort of build a resource theory, and you view this entanglement as something costly as a resource, right? And then so this entanglement that cannot be generated via some operations that are defined to be cheap or free, in particular by this local operations in classical communication, and you actually need this elementary entangled pair as a resource, for example, Bell pairs. And besides quantum entanglement, which is probably already well known at this moment, it turns out that there's another layer of quantumness that is defined, or that is revealed in the sense of the hardness of classical simulations. I think it is also well known at this point that there exists highly entangled states as well as entangling dynamics that can nevertheless be efficiently simulated classically. And since there exist such states, so another layer of quantumness really has to do, it's really essential for this quantum advantage. And what I mean by this, the class of highly entangled states, but classically simulable, let's consider this something elementary. It's just the Clifford unitary. So the Clifford unitary refers to a restricted set of unitaries that has a special property that it maps a single Pauli string to another single Pauli string, but it never, without ever generating superpositions among the Pauli strings, and which is in general not true for generic unitary evolution in the Heisenberg picture. And these are the well-known examples of the sort of the single qubit and two qubit operations that belongs to the Clifford group. So you can actually check that they indeed have have this property that they map single Pauli operators to another single Pauli operator without generating superpositions. And it turns out that these, the Hadamard S and C NOT gate generates the full Clifford group on n qubits. And it's just a brief review. So since the Clifford unitary has a special property that it preserves the structure of Pauli strings, so we could imagine that there are a special set of states that can be tracked or it can be specified by this list of Pauli strings, and these are actually the so-called stabilizer states. And so basically, the punchline is like quantum states that together with Clifford operations can be simulated if classically these are known as the stabilizer state. So basically, let me just briefly introduce the notion of a stabilizer group S. The stabilizer group basically is an abelian subgroup of Pauli of n-qubit Pauli operators that stabilizes a quantum state, meaning that when acting on a quantum state, it basically returns the quantum state with eigenvalue +1 for any element belonging to the stabilizer group. That's the definition. And just two concrete examples. For example, you can have this all zero state, and then the stabilizer group it's generated by these elements Z1, Z2 to Zn. That's the generator of the stabilizer group. And this is a product state, of course, but you can see that there can also the stabilizer states also include entangled states. For example, this is the Bell pair state 0, 0 plus 1, 1. And then you can easily check that the stabilizer group is generated by Z1, Z2, and X1, X2. You can directly verify that it satisfies the property, and then you can generate the group by taking products of these two generators. And also by this famous Gottesman-Kneel theorem, we know that stabilizer states plus Clifford operations can be efficiently simulated on a classical computer. So, okay. Since we know that there exists this special set of unitary and then also this special class of states known as stabilizer states, but of course, these are highly special states that are not the majority of states in the Hilbert space. So there is this notion of quantum magic, which basically quantifies the degree of non-stabilizerness, basically quantifies, how far away is your state from any stabilizer state. And this is the notion of quantum magic. So basically, it quantifies the amount of non-stabilizerness in a given quantum state. And as a concrete example, it's the example that people usually talk about. It's basically, suppose I have a plus state, and then I apply a T gate, and the T gate is actually not a Clifford unitary because you can directly check that it doesn't have that property of the Clifford unitary, and then you generate a state that is not a stabilizer state. So this is actually a magic state. And this kind of magic states turns out to be essential for universal quantum computing because it is also well known that the Clifford unitary is not sufficient for universal quantum computing. But then when the Clifford unitary, together with the T gate, you can actually generate the universal set of unitaries. And also, magic states are also kind of, you can view this as a resource. It's kind of costly in the sense that very often in the context of fault-tolerant quantum computing, these type of magic gates are hard to implement transversely. So you can actually view this. You can actually have a resource theory where you kind of view this magic as a resource, and then the Clifford operations as a free operation. So okay, this is the notion of quantum magic. Basically, it quantifies the degree of non-stabilizerness, but this is kind of still vague at this point. So we need a concrete measure for quantum magic. So here I'm actually giving a sort of a list, a very like a highly incomplete list of magic measures. So that involves, for example, if you look at the first line, relative entropy and trace distance. These are sort of like distance measures because, as I said, quantum magic basically measures the distance of a given state from the set of stabilizer states. So basically here, you can actually see that the relative entropy is basically to find a state that belongs to the convex hull of the stabilizer states, and you measure distance in terms of the relative entropy, and then you minimize over all the sigma belonging to the set of stabilizer states. And the second one, trace distance, is very similar. It's just like you pick a different measure for distance. You actually use the trace distance instead of the relative entropy. And also you can sort of define this kind of stabilizer rank by trying to decompose, by actually looking at, how many, if you try to decompose the state in terms of a set of stabilizer states, how many stabilizer state you need. And also there's the free robustness and also Wigner negativity and the associated mana. So these are quantities that people have already defined in quantum information and magic resource theory that because to define a quantum a sort of a good measure for magic, it has to satisfy, in resource theory, it has to have this a list of good mathematical properties. For example, it has to satisfy monotonicity, meaning that under free operations, it's not increasing, and also it's faithful, that in the sense that it returns zero if and only if the state is actually a stabilizer state, etc. So they actually satisfy all these nice properties, so that you can actually prove various bound, and then like in resource and quantum information theory. But the thing is that, at least to me, these definitions, especially if you look at the first two lines, that seems a little bit daunting to me, because very often I just want a number. Like if you speak of distance, I just want to get a number. But then, all these definitions actually involve this minimize, this min, and then also this supreme, whatever. These notions, I know what it means, but it scares me until today. So if you want to get a number, there's actually another measure for quantum magic, which was actually, I think I heard that it was actually, people know this actually from a while ago, but formally it was actually written, first proposed in this paper by Alyosha and company in 2022. This is the so-called stabilizer Rayleigh entropy. So this is actually a computable, although not efficiently computable, it's a computable measure, meaning that I can get a number that doesn't involve a minimization or an optimization over all states in the set of stabilizer states. So basically, the definition of the stabilizer Rayleigh entropy, this is something we will be using, or a related quantity rather. So the definition is the following. So for pure state, I'm only going to be talking about pure states, by the way, today, because for mixed state, I don't have much to say. So for pure state psi, this is the definition of the stabilizer Rayleigh entropy. The structure looks very much similar to the usual Rayleigh entanglement entropy, and then there is this Rayleigh index alpha. And here, it's basically, you take all the Pauli strings, and then you look at the expectation value of the Pauli strings under the state, and then you raise it to the power alpha, and then you sum over all the Pauli strings. So this is like it looks like a Rayleigh entropy. That's why it's called the stabilizer Rayleigh entropy. So let's just try to get a little bit of intuition about this quantity. So we can easily check that for stabilizer states, this quantity is zero. And that is because for stabilizer states, well, for pure states, right? Mixed state, you need something else. But for pure state, I didn't touch it. Okay. So for a pure stabilizer state, out of all the 4 to the n Pauli strings, you get exactly 2 to the n Pauli strings, where this quantity gives you 1, and then it's 0 for all the other Pauli strings. So you get exactly, this thing gives you 0. And for an arbitrary state, it turns out that the expectation value of the Pauli strings under the state satisfy this very simple normalization condition. And once again, for mixed states, this is no longer true, but for pure state, you can actually check that it satisfies this normalization condition. So you can actually view this quantity as a probability distribution, because it's squared, it's always positive. And then so you take this probability distribution and then you compute its higher moment. So it's like, it's actually probing, how delocalized is that probability distribution over all Pauli strings. And this is the intuition behind this as a measure for, how far away from being a stabilizer state where this distribution is sharply peaked around the set of stabilizer generators. Okay, so see, now we sort of have the landscape of quantumness characterized by these two complementary aspects. So on the one hand, you have entanglement as one axis, and then on the sort of okay, sorry, it's fragile. Okay, so sort of on the vertical axis, you have magic, and then actually you can actually put some sort of representative states or a class of states in four of these quadrants, right? So you can have states with low magic and low entanglement, which are, product states like this. But then you could also have, low entanglement states, but with high magic, which are, for example, the random product states. And then you can also have, highly entangled states, but not magical. These are like highly entangled stabilizer states. And then, of course, on the other extreme, you can have hard random states that are both highly entangled and also magical. But the question that we're trying to ask, okay, so here is the thing. So ever since I should mention that this notion of stabilizer radiant entropy, since I mentioned it's computable. So ever since that paper that proposed the stabilizer radiant entropy, this field of quantum magic has really, in the many-body setting, has really taken off. So what I've been seeing is that everybody, they basically dug out their favorite model and then run the simulation and then just compute the magic for whatever reasons. I mean, which is fine if we're still trying to understand something and we're at the stage of collecting data points. But I just want to take a step back and understand something simpler. So I draw this in this figure as entanglement and magic as two sort of orthogonal directions, but do they actually have some is there any interplay between entanglement and magic in a dynamical setting? So what I mean by dynamical setting is, so what is the role of entanglement in facilitating the growth and spread of locally injected magic? So suppose I inject magic in the local region on a given state. So how does that spread? How does the magic spread across the entire system? And what is the role, or if there is any role, that an entanglement is playing in facilitating the growth and spread of locally injected magic? Okay, so actually this is actually a simple example. Maybe it's not the best one, that which is the reason that I started thinking about this problem, is just a very simple example. So in both cases, I'm actually applying a single T-gate to a stabilizer, to an initial state that is not magical. So in the first case, I consider my initial state to be all plus state, which is a stabilizer state that's not magical. And then I apply a T-gate somewhere here. And then this is my final state. And as an observer, if I look at the subregions of my final state after the application of this T-gate, I can easily spot, okay, this is here. This is the qubit where the system is magical, because everywhere else I'm going to see a plus state. So I can immediately tell, okay, I basically inject magic by applying a T-gate here. And in the second case, I'm still applying a T-gate to a non-magical state, which is a GHZ state. And after the application of the T-gate, the state becomes magical. But then the thing is, as an observer, when I look at any local subregion, I see a maximally mixed state that is non-magical. So it seems like even though in both cases I'm actually injecting magic locally by a sort of the same gate, whether that magic is locally detectable is actually quite different in these two scenarios. And the reason is basically because, in this case, I'm actually starting from a product state. And in the second case, I'm actually starting from an entangled state. So it seems like there is some role played by entanglement in sort of spreading out the magic that I injected locally to the entire system that is sort of hidden to any local observer. So basically, I just want to quantify this in a sort of analytically tractable setup. So this is the setup that we chose. So I said that I'm gonna be focusing on pure states. So I consider a pure initial stabilizer initial state rho psi that is partitioned into two subsystems A and B. So initially, of course, as a stabilizer state, there's no magic. Their initial state can be highly entangled. So this is my initial state. And then I apply a hard random unitary on the local subregion A of the system, thereby injecting magic, right? It may appear, this UA may appear non-local because I'm actually considering a global hard in the local subregion, but actually it's fine. If A is way smaller than B, I can actually do that. So what we are doing is that we compute the, in this simple setup, we compute a quantity that is closely related but not the same as the stabilizer Rayleigh entropy that I just introduced. So it's basically the stabilizer Rayleigh entropy without the log. So it's some quantity called the linear stabilizer entropy is defined in this following way. So it's basically without the log, but it's something tricky because you know, if you look at this quantity, for stabilizer state, this quantity is actually one, but for non-stabilizer state, this quantity is actually smaller than one. So remember, it's actually the reverse. Like the more magical your state is, the smaller this quantity is. You could have defined something by this linear stabilizer entropy by defining this to be 1 minus this y, but I just don't want to bother. So remember, the smaller this thing is, the more magical the state is. And for stabilizer state, this quantity is just 1. And actually, this quantity satisfies also many nice properties under in the sense of resource theory, in the sense that it's faithful and it's invariant under Clifford, and it's multiplicative, and actually it's a strong monotone under free operations for at least in this way. Yes. Um, that's an I did okay. To, I would the only thing I know right. It's actually more subtle than that because I think the only thing I know is that if you consider something like the for example the non-local magic or something like that that is sort of related in the sense of whether your state is classically similar. It can be efficiently classical. Yeah. Okay. No, but I think he was asking about the classical the efficiency of classical simulability, not in terms of the previous measure. Uh-huh. Yeah.
So, where you can trace B.
Where? Here?
Trace B.
No. That's the global magic. Yeah. That's the magic for the entire system. So I'm only injecting magic in the local region, but then I'm computing the magic of the entire system. Yeah. Okay, that's one thing. Yeah, I'm not tracing over subsystem B, and then I'm actually, yeah.
Then I have a question.
Mhm.
Because feel like if there's any metric of magicness for even pure state,
Mhm.
more or less, I guess they should roughly agree how many T states we can distill or something.
Mhm.
But then, are you saying that like that can like change depending on like the localness of the magic, or
Um, Mhm.
Yeah, so use the global methods and the number of figures to show like global operations. Yeah, so that inclusion is definitely right. Yeah, but maybe the local storage here is more like you cannot distill anything local.
Right. Yeah. I'm sorry. Yeah, I can define this for reduced density matrix, but uh, yeah, I can define that, but there are two problems. The first, well, I would say problems. So the first one is that um, in the case of mixed state, if you have a reduced density matrix, then this quantity is no longer the normalization condition is no longer satisfied for because that normalization that I had, which is crucial if you view this as a probability distribution that relies on the fact that you have a pure state that trace of that squared is actually one. But then for a mixed state, it's no longer satisfied, and then you have to modify the definition of the stabilizer Rayleigh entropy, and that's number one. And number two is that uh, some of these nice properties in the sense of resource theory that I listed here, it has only been proven for pure states. Yeah. So for mixed state, it seems like there are some issue with the whether the stabilizer Rayleigh entropy or even this linear version of the Rayleigh entropy is actually a good measure. But yeah, so that's why I'm only sticking to pure states in this case. Yeah. Okay. So this is the setup. And as I prompt, okay, I should mention something. I should just comment on something that I want to say about the setup is that this setup actually sort of it separates the two processes of, if you want, of entanglement generation and magic injection. Because the thing is that if you fix your bipartition A and B, since you only apply the unitary on subsystem A, it no longer changes the entanglement between A and B, and nor does it change the entanglement spectrum. So somehow I'm actually separating these two processes of entanglement generation and the magic injection. So basically entanglement is pure stabilizer entanglement, at least with respect to this bipartitioning. And that is kind of encoded in my initial state. And then UA just inject magic while preserving the entire entanglement spectrum. So I just want to separate these two things. So this is basically the result. So we're actually computing the average linear stabilizer stabilizer entropy averaged over the hard random U, and then this is basically the result. And here, A is the size of the subsystem A, and then E is the entanglement entropy between A and B. So remember, I told you that for stabilizer state, this quantity is 1. And then the smaller this quantity is, the more magical the state is. And you can see that as promised, somehow this entanglement that is in the initial state shows up here automatically. And these are just the subleading corrections. So you can think of this result as the sort of the leading order results in the limit where the size of A is larger than 1. But shortly, I will show that the A doesn't have to be like the size of A doesn't have to be like crazily large, because you only need the Hilbert space dimension of subregion A to be large rather than like the linear size to be large. And that is, for moderate systems sizes of A, it's actually good enough. So this is basically the result. Yes?
Value is A, right?
The maximum value of, right, yeah.
So this expression, like if A is 1,
Uh-huh.
one side,
Uh-huh.
then
this expression doesn't hold, I think. Yeah.
Y bar is 1.
I'm sorry?
In this case, Y bar is 1.
That you have to be careful because I'm actually dropping something here. So yeah. Yeah.
Previous, the like little toy example.
Uh-huh.
Both the stabilizer and be like 1/2 and 1/4.
I'm sorry?
In the
Previous.
state,
Uh-huh.
like 1/2, like previously with you get 1/4. Is that
I suspect that actually no, that example is probably that's why I'm saying it's probably not the best example. This is just to illustrate that the delocalization of magic. But I think if I remember correctly, I think if you compute this this linear entropy for the final state in this, I think you probably get the same answer in these two cases because I think in either case, you destroy precisely one stabilizer generator by locally injecting a T-gate. That would be my suspicion, but I have to double check. Yeah. This is not a good quantitative demonstration, but I think that's the, okay. Okay, so let me just briefly explain this result, like how these various factors come around. So if I just temporarily forget about these higher order corrections when the size of A is large, so you have this prefactor like 4 times 2 to the minus A minus E. So how to understand this prefactor? Well, I can just break down this 4 into 1 plus 3. And this 1 is actually coming from the following. So because I'm only applying the hard random unitary to subregion A, I'm actually only destroying, so I'm actually leaving, I'm not touching the subsystem B. So I'm not destroying any stabilizer elements in the stabilizer subgroup of B, right? And then if you count, so these are the elements in SB will survive, and they will contribute 1 to the average Y. And then if you just count how many surviving stabilizer elements there are in the subgroup of SB, and then you find that that's precisely this value. And if you remember correctly, the entanglement is basically B minus the rank of the SB. So this is basically, you do that in reverse. And when you divide it by the normalization 2 to the n, that precisely gives you this 2 to the minus A minus E. And then this 3 is actually, in some sense, non-universal. Well, in the sense I'll explain. So these are the contributions from other polystrings besides those that are only supported, that belongs to the stabilizer subgroup of SB. Why do I say that this 3 is non-universal? Well, because you could also generalize this definition of linear stabilizer random entropy by raising not to the power of 4, but to alpha. And so this 3 is actually going to depend on this alpha. And in particular, you could consider this alpha going to infinity limit, and then only this one will contribute in this limit. And then in this case, you get precisely this answer without this contributions from other polystrings. Okay, I hope this is probably clear. So, okay, we have an analytical result. So here is basically a comparison with numerics. So the dashed lines are basically this analytical results, and then these triangles are numerical simulations. So let me just briefly say how the numerics are done, because we know that because we wanted to draw some stabilizer states, while at the same time controlling its entanglement entropy. But we know that for a bipartite stabilizer state, it can always be brought into a collection of Bell pairs spanning subsystem A and B, and plus some single qubit states in A and B. And so I can choose that state as my initial state to begin with without loss of generality, because I can always recover that state by applying UA tensor UB, where the UA and UB are Clifford, and then the UA can simply absorb in the hard randomness, and then UB is not changing the magic, so I can just drop it. So you can actually see that well, the agreement is kind of perfect, and then you do see some deviations when the size of A is actually small because we're only keeping the leading order terms. But actually, you see that you already see pretty good agreements even when the size is like moderate. So it doesn't have to be. I mean, even though I said the size of A is larger than 1, but it doesn't have to be like crazily large. So a little bit of technicality. I'm just briefly flashing how we obtained this result. So the calculation is done by realizing that the density matrix of the initial state can be written as a projector. Basically, it's a sum over all elements in the stabilizer group. And we can actually make use of this following sort of coset decomposition of the entire stabilizer group SAB in terms of its subgroup, SA tensor SB. And so, yeah, this is basically the coset decomposition. And this is the subgroup. And then you can convince yourself that this AI and BI, they are actually nothing but the logical operators of A and B. So actually, when the entanglement entropy is between A and B is E, you can think of this as encoding E logical qubits, and then there are precisely 4 to the E logical operators. And well, you can actually check that the dimension match, and then you can convince that yourself that this decomposition actually works. But still, just to give a very simple example, you can take a 5-qubit GHZ state, and then you can list precisely what are these SA and then SB, and then you can see that well you have the logical operators in A and B, and then you can actually decompose the entire stabilizer group in terms of the cosets. And then, okay, and then you just notice something really simple, that the Pauli string can be written as PA tensor PB, and then also that UA only acts on the subregion A, and then you can plug this coset decomposition in the expression for the rho, and well, you get something that belongs to subsystem B, which is not touched by the Clifford, but by the unitary, and then you get something that involves an average over Haar random unitaries in A, right? And here, notice that because the cosets are non-overlapping for each PB, it's going to overlap with at most one cosets, and then basically, well, you keep track of all the multiplicative factor, and then for this thing, it basically involves an average over 4 copies of UA and UA dagger, which are Haar random unitaries, and we can just use our favorite Weingarten expressions, even though in this case it's kind of a little bit crazy. Yeah, I mean, this is actually a diagrammatic representation. Has anybody seen this type of diagrammatic representation for the Weingartens before? At least this is my first time of seeing that, because usually nowadays you draw this as a stack of U and a stack of U dagger, and then you connect them with lines, right? So, but the advantage of this one is because in this calculation we really need to keep track of the what are the leading order contributions, and that has to do with like the cycle structures of the 2 permutations. But in the usual drawing, we don't really, like, you have the sigma, you have the tau of the 2 permutations. It doesn't really, you can't really see clearly the cycle structure of the sigma inverse tau, but this one, you can actually read off from that. So we just prefer this representation. Eventually, this is how you get the results. Okay. So we also consider some other setups. So previously, I told you that I'm only applying a Haar random unitary on subregion A and without touching B. So here, but this is not the most general approach of magic injection while preserving the entire entanglement spectrum. So we did a second setup, is that we apply a factorized unitary to the entire system. So we apply a unitary, which is a UA tensor UB, where UA and UB are independent Haar random unitaries, and then we compute the average Y of the final state. And then this is the result we get. So let me just briefly explain what is interesting about this result. So you can see that we get this 4 times 2 to the minus n and 1 plus. So if I don't look at this thing, forget about the second term and forget about everything here. So this 4 times 2 to the minus n is exactly the average Y for a Haar random state. But which wouldn't be surprising had I applied a global Haar random unitary on the entire system, because then I turn this into a Haar random state, I precisely get this thing. But then, of course, there's deviation, because I'm not really applying a genuine, a global Haar random unitary, so I'm going to get deviations. But then the deviation is exponentially suppressed in the amount of entanglement between A and B. So what does it mean? It means that, well, suppose as long as my initial state is sufficiently entangled, then from the point of view of magic, even though I am actually applying a factorized unitary, the magic actually pretty much saturates to that of a Haar random state. So it almost sounds like, with moderate amount of entanglement, this factorized unitary actually resembles a global Haar random unitary. So it's another example of how the stabilizer entanglement actually facilitates magic saturation. Yes.
Actually, if there was a Clifford type entanglement between A and B,
Mm-hmm.
and if you inject one T state,
Mm-hmm.
then does the number of distillable T states, is it larger than having a less entanglement between A and B? So my question now is whether it's a stabilizer entanglement, the metric you're using is a faithful, I don't know, a meaningful interpretation in the sense that, if So I think basically what you're saying is that when A and B has a less entanglement,
Mm-hmm.
then injecting magic on A,
Mm-hmm.
the overall state has a less magic than
Right.
when A and B had a larger Clifford entanglement.
Mm-hmm.
Then now my question is, okay, so your Y bar, if it's
Mhm.
smaller for the latter case,
Mhm.
then does it mean that there are more maybe key states you can distill out of this state, or how should we interpret this?
No, I don't have a concrete answer in terms of the like the distillation rate because I'm not familiar with all these bounds and measures in terms of the magic measures in the resource theory. Maybe I think Zwen is more familiar with that. But I think that's then, yeah, do you want to say something?
Yeah, the answer is no.
Mhm.
Okay, so then what did really increase? What's the magic is that really saturated or decreased in this set?
No, it doesn't. So okay.
I guess one of the point here is that it becomes super novel, right?
Yeah, so but in terms of the sort of yeah, I think it doesn't change the amount of T gates that you can distill because you're basically applying in terms of resource, you're actually injecting the same kind of resource. Yeah.
So then
Mhm.
when you interpret specializer
Mhm.
this measure of how he localizes
This is what I'm trying to get to, because right, yeah, and also if you know sometimes people define this notion of non-local magic, meaning that the kind of magic that cannot be undone by applying this type of factorized unitary. So in that sense, of course, you could say, well, this way of injecting magic, there's no non-local magic because I can always undo it by applying the inverse of that. But and also you can see that this UA tensor UB doesn't change the entanglement spectrum. You still have a flat entanglement spectrum, so there's no non-local magic. But I mean, operationally, yeah, this is yeah. And also because this is the only measure that I know how to compute analytically, I don't, yeah. Okay. And yeah, and this is just basically another numerical test on this one. And then you can see that in order for the final state to resemble a hard random state from the point of view of magic, you actually don't need E to be extremely large. It's basically larger by a constant is already basically the magic of the final state already saturates to that of a hard random state. And we also compute that. So I'm only going to be flashing these results. So we also generalize this setup to a tripartite entanglement, meaning that instead of partitioning the system into A and B, we partition into A, B, and C. So we know that for a sort of a tripartite Clifford state, stabilizer state, sorry, it can always be brought to a collection of GHZ states spanning the entire system and EPR pairs between each system and then some single qubit states. So this is basically how we are going to specify our initial state. And then in this case, we can actually play the same game and then compute the average stabilizer Rayleigh entropy. And this is basically the result. And well, the details are not so important, but just to look at the prefect, the various factors appearing in the exponents. So basically, if you look at here, this G, B, A, C, B, B, C, that's exactly the amount of entanglement between A union B and C. So basically, this sort of resembles the result that we obtained in the first part. And then the second part, of course, this would have been absent if the entanglement between A and B is large, meaning that the UA the factorized UA tensor UB would act as if I had applied a hard random unitary on the entire subregion AB, provided they are sufficiently entangled. So in some sense, this result is actually a combined effect of the two previous results. Okay, and then this is UA. Yeah, but okay. Next, I want to previously, basically, we injected magic by applying a sort of hard random unitary within a subsystem. So here we actually consider something else. We consider, of course, we didn't do this super systematically, but at least we want to show some preliminary results on what if I inject magic instead of with a hard random unitary, but with a shallow depth breakwork circuit. So basically here, I take we basically take a brickwork circuit of various steps and also involve different gate ranges. And so we compute the average y as a function of the entanglement. So you can see that qualitatively, this feature is still there. So basically, the more entangled the state is, even though we are not doing a random unitary, it's still decaying with the amount of entanglement. But it's just that in certain cases, when the circuit is too shallow, actually it saturates somewhere without further decaying, meaning that, well, maybe the circuit is too shallow to saturate the average y of a random state. Yeah, so here basically we can actually take an initial state to be the Bell pair state, but then since we're not applying a random unitary in A, this is not a generic choice, but we can always recover a generic stabilizer state by applying a sort of a Clifford unitary within A, and then apply the random gates in the brickwork circuit in system A. Okay, finally, this is the last thing I want to talk about. So we sort of chose initial stabilizer state to begin with for a good reason, because we want to control we want to control where the magic is coming from and then where the entanglement is coming from. But it's a fair question to ask, what if the initial state that I start with already contains magic as not a stabilizer state? So does anything change? So of course we didn't exhaust all possibilities. We just considered two special classes of non-stabilizer states. But because we also want a way to sort of systematically tune the entanglement. So the first one is we consider my initial state to be k imperfect Bell pairs. So instead of a perfect Bell pair, I just take an imperfect Bell pair and then I make k copies of that. This is my initial state. And in the second case, we just consider some superposition of tensor product of I and A and B. These are just computational basis states. And I can play directly with the entanglement spectrum. I take this, so this is no longer flat. I can take the entanglement spectrum to have various distributions. I take that as my initial state. And then I can look at the average magic numerically. So let me explain to you what we're seeing here. This is the result. So these two figures basically correspond to the two classes of initial state that I'm taking. So this is for the imperfect Bell pair states. And then here, this is for cases where I play directly with the distribution of the entanglement spectrum. So you can see that, well, roughly, that you still see the same trend that even in this case, that the average y is actually decaying sort of exponentially with the entanglement entropy, even though the state is not perfectly a stabilizer state. But here, you actually have to be a bit careful because previously, because the initial state is not magical, I can just compute the average y for the final state. But here, since my initial state already contains magic, so I have to be careful in sort of interpreting, where, the fractions of magic that is being injected versus those that are already present in my initial state. So basically, this is what these two groups of plots are for. So, right, so the dashed lines are basically the average y of my initial state. And then the solid lines are basically, I subtract, well, in this language means division, means my subtraction. So the average y of the final state divided by the average y in my initial state. And then you can see that without looking at the caption, you can actually see that the order of the colors are kind of reversed. And I think this is something quite interesting because it seems like the more magical my initial state is, the less magic that I can inject via this subsequent random unitary. So I'm not sure whether this is a well-defined quantity, but it seems like there's some notion of magic capacity that decreases when the initial state contains more non-local magic in this case. So just the order is kind of flipped. Is this clear? Like what I'm trying to say? Okay. Yeah, so as promised, I'm concluding here. So basically this is the main message is very simple. It's like the stabilizer entanglement functions as a highway that sort of facilitates the spread of local injected magic. And when we consider non-stabilizer entanglement, it seems like the there's a notion of magic capacity of a given state that depends on both its entanglement and sort of the non-local magic that is present in the initial state. And then, of course, there are various open questions. I think somebody already asked some. But yeah, that's basically all I want to say.
Thanks for the nice talk. So, you calculate for the linearized entropy for the magic. So it seems like already the calculation is painful. So, but anyways, do you think this general statement holds for generic measure of the magic, or is just a special case of linearized entropy?
Yeah, this is one of the open questions that we're not sure, especially if you consider certain measures that can be converted to various bounds of the distillation rates of the T gates, then it probably is not, yeah, I don't know. Yeah.
Thank you.
So thank you for nice talk. Your analysis mainly focus on focus on injecting random interval.
Right.
But if you consider like tensor product of plus state, then applying single qubit T state on two of these qubits, you have two magic states. But in contrast, if you have GHZ state, if you apply two T gates on two of these qubits, you just have another stabilizer state, right? So the relation between magic and entanglement in this observation might be a bit like contradictory to your observation in a sense, no? Like so
yeah, because this is all, under Haar averaging, right?
How random. So
yeah, how randomness, because you can always, like in your example, I mean, even though, okay, like you could say, well, even like in the GHZ case, I don't really know, for a local observer, I don't really know which, where the magic is, but I don't care. I can always just undo it by applying something else on wherever separation can just undo it. So yeah.
Yes, so my question is basically, so you worked on how random interval to extract to investigate some relation between stabilizer entanglement and magic. But in the most general case, if you can choose non-conformal gates and the initial states, then what would be the more broadly applicable approach that you could consider to obtain a more generally applicable conclusion between the relation of magic and entanglement. So my point is that your analysis is applicable only in the case of hard random interval, but may not be applicable to the case of
for a particular case, this is probably not the best quantity. Yeah.
Or would there be a better approach to be able to be able to be applicable to more general case? What do you think? I'm just
no, I don't have anything concrete in mind. Yeah.
Thank you.
Any more questions? Okay, if not, let's thank the speaker again.
Thank you.
So